For question number 10b, we can use something called an integral test, which is something that we're going to learn a little bit later. And the integral test essentially is this. We can say that the sum of the series of 1 over n to the of 1 over n log n to the power of p, we can say that series is the sum is similar, or at least behaves similarly in terms of convergence, divergence, to the area underneath an integral. So what I can say is I can have a function y is equal to 1 over x log x all to the power of p. And what we're going to say is that this graph, the area under this graph, is going to behave similarly to the sum of this series. So you can imagine the sum of the series would be just these bars under a graph, bars along discrete sums or bars, rectangular bars, and we can think of the area under this curve as kind of the area under that discrete function. So an example might be this. I have a series that could be represented by these bars, and then we have a function, and that area under that integral is going to be similar to the area, the sum of those bars. Okay, they're not actually the same, but they're similar. Okay, so this is the idea behind this, what we call this integral test. So what I can do is I can integrate this expression, and it will tell me something about the series. So I'm going to go ahead and integrate this expression. So I'm going to find the area under this curve from some arbitrary point. I'm just going to start at 2 to infinity. So since it is to infinity, I need to use a limit. So limit as a approaches infinity from some starting point 2. And I could choose any starting point because we're just seeing if we have a finite sum or not. So if it has a finite sum from 2 to infinity, then it must have a finite sum from any other arbitrary starting point to infinity. Okay, so then I'm going to have this 1 over x log x to the power of p. And I'm just going to put the p in a different color here. That p, we need to then decide what that's going to look like. Okay, so we're going to do substitution. So I'm going to need a dx in here. So I'm going to let u equal log x, and then du works out to be dx over x. Okay, and we can see that we have the dx over x to be able to get rid of all the x terms in this limit. Okay, so then I'm going to do my substitution here. I'm going to do the limit to infinity from some arbitrary point to infinity. And then I'm going to apply my substitution. I'm going to have 1 over u to the power of p. And then I can just replace the 1x dx with a du. So I'm just going to get rid of that and replace that with a du. Okay, so this is something I can integrate. Now we have to look at different cases here. So if p is 1, then we have to use log. Okay, so we're just going to do that case first. And if p is not equal to 1, we can use power rule. But really the log is going to, p equals 1 is going to be our boundary case. So we're going to let p equal 1. And maybe I'll do this I'll just do that in black. So we're going to just let p equal to 1, and then we're going to do this problem. So we're going to find the area, the limit as a approaches infinity from 2 to infinity of du over u we know that this is going to be, oh, sorry, I have to remember that when we switch our variables to maybe make sure that that is in terms of u equals a, and u equals 2. Okay, and I'm going to integrate this as with my log. So limit as a approaches infinity, this is going to be log of u from u equals 2, sorry, x equals 2. What am I doing here? Okay, so the proper notation is I have to state that this is in terms of x's because I've changed to u's. Okay. So this is when x is equal to 2, because that's what I started with. X is equal to 2, and x is equal to a, x is equal to 2, x is equal to a. Okay, and then I'm going to replace my u again, so I get limit as a approaches infinity of log x. And I'm going to do this from 2 to a. Okay, so then now I can apply my, I'm just going to do my substitution first, and then I'm going to apply my limit. So log of ln a minus log of ln 2. Okay, that's my integral, my definite integral. I'm going to then replace my a with infinity. So log of log infinity minus log of log 2. Oops, this is log of log 2. Okay, so in doing this, I can see that I have log of log infinity is infinity, log of infinity again is infinity. So I know that is infinite, and that's going to be subtract whatever that amount is. But whatever that amount is, all we really care is the fact that it's a finite amount. And so the net area is infinite. So what does that mean? What can I conclude from that? Well, when p is equal to 1, it is divergent. Okay, so when p is equal to 1, in this case, it is divergent. Okay, and if p is equal to 1 is divergent, then we can also say that p is less than 1, it would also be divergent. So this allows me to establish that p less than or equal to 1 is divergent. Okay, so that is, we still haven't determined when it does converge. So the question is asking about converging. Okay, so I'm just going to do the same problem. Actually, I'm going to just move that over to the other side. So when p is less than or equal to 1, we're going to say it's divergent. Okay, so we're going to let p be greater than 1. Okay, and we'll do the same thing. So when p is greater than 1, we end up with a is equal to limit as a approaches infinity from x is 2 to x is a, and this is du over u to the power of p. Okay, maybe I'll just make that in red. So all I've done is done the same thing, but now I'm going to, because p is not equal to 1, I could use power rule. So then this becomes limit as a approaches infinity. Using power rule, I get this is going to be negative p plus 1. So I'm going to write this as 1 minus p. So negative p plus 1 is same as 1 minus p. Remember to divide by 1 minus p. Okay, and then we're going to evaluate this from x is 2 to x is a. Okay, I'm going to substitute back in my log. So limit as a approaches infinity. This is going to be log of x to the 1 minus p over 1 minus p, and that's from 2 to a. Okay, so then plugging in my infinity in here, I'm going to end up with log infinity, okay, to the 1 minus p over 1 minus p minus log 2 to the 1 minus p over 1 minus p. Okay, so again, for the right-hand side of that, really this is the fact that this is finite is what all we really need. So we just know that this is finite. Okay, if p is some whole number, okay, bigger than 1, so it's going to be finite. So that's not really an issue here. It's this other part here. And that other part there, let's take a closer look at that. This other part, the 1 minus p is really not significant in the denominator as long as it's not equal to 0 and p is not equal to 1, so it's not equal to 0. So when I look at that part there, it looks like this. I really want to know what's happening if it's going to converge to 0. Okay, and in fact it does. We have this, if we do this, we're going to have if log infinity is infinity, and we're going to, since p is greater than 1, that exponent, this exponent here, is going to be negative. A negative exponent means that expression is going to be in the denominator. So what ends up happening is we end up with that infinity in the denominator. Log infinity is just infinity, and that becomes some power of some positive power. Okay, which maybe I'm going to write as, give it another variable, k, where k is greater than 0. Okay, k is a positive power. And we end up with that, and then we still have that 1 over 1 minus p. Again, that's not really significant. Again, we have this finite value here. And we end up with 1 over infinity is 0. So we end up with 0 minus some finite number. That finite number is going to end up being positive because of log 2. That log 2 is going to end up being negative, so it's a negative finite number anyways, so we end up with a finite number. Okay, therefore, that means then that for p is greater than 0, so p is greater than 1, which we stated here, that for p is greater than 1, that it is convergent. Okay, since the area under the area under the continuous function is finite, we're going to say that that sum is also finite. Okay, it's not the area and the sum aren't the same, but if one behaves in one way, the other one will behave similarly. So for what values p does this converge? For p greater than 1, we can say it's convergent.